This video is for ELEC 2132 Circuit Analysis 1, and the topic of this video is source transformations. A practical voltage source is an ideal voltage source here with value V sub S that has a resistor R sub S in series with it. A practical voltage source is often necessary because an ideal voltage source, V sub S, when shorted, will produce an infinite current, I equals infinity, implying an infinite amount of power supplied, and is therefore not realistic. In the case of a practical voltage source, the current supplied when shorted is going to be V sub S divided by R sub S, which is non-infinite and therefore more realistic. Now, if I connect a load resistance across this practical voltage source called R sub L, the current I sub L that is delivered to the load resistor is going to be equal to the voltage value divided by the total series resistance R sub S plus R sub L. The voltage delivered to the load resistor, V sub L, is going to be equal to V sub S times R sub L divided by R sub S plus R sub L, because it's simply a voltage divider. A practical current source, additionally, is a current source that's ideal, I sub S, in parallel with a resistor, R sub S, because a current source, I sub S, that is connected to an open circuit will create an infinite voltage, therefore supplying infinite power, and that's not a realistic scenario. So, a practical current source like this, when connected to two open terminals, no longer creates an infinite voltage. The voltage instead is I sub S times R sub S. And so let's then connect this to a load resistance, R sub L. The current delivered to that load resistance, I sub L, is going to be equal to, well, it's a current divider now, so it's going to be I sub S times the ratio of the conductance of the load to the total conductance, which is equal to I sub S times R sub S divided by R sub S plus R sub L. The voltage delivered to the load is I sub L times R sub L, which is going to be I sub S times R sub S divided by R sub S plus R sub L times R sub L. Okay, so now let's compare the behavior of these two circuits with respect to the load resistor. I've rewritten the equations that I derived on the previous two slides here for I sub L and V sub L for each circuit. Now what you can see is that the two I sub L equations will be equal if V sub S is equal to I sub S times R sub S. So V sub S is going to be equal to I sub S times R sub S. Now, if we take the equation that we just derived and substituted in here, we get that V sub L is equal to V sub S times R sub L divided by R sub S plus R sub L, which is the same equation that we had for the voltage divider. Which means now that these two circuits are completely equivalent with respect to the load resistor. It doesn't matter which one of these you use. You could use either the voltage source or the current source, and you would get the same voltage and current at the load resistor as long as you use this conversion between them. Alternatively, you can convert the other way by saying that I sub S is equal to V sub S divided by R sub S. So this means that if you're only concerned about the behavior of a load resistor and not the circuit that exists around it, you can keep transforming sources until you can get to a very convenient analysis method for the load resistor. So let's do an example problem. In this problem, we are tasked with finding voltage V sub X, which is across a 20 ohm resistor, and that will basically act as our R sub L. We have an entire other circuit network consisting of a 20 volt source, a 10 ohm resistor here, 15 ohm resistor here, 14 ohm resistor here, and that is going to act basically as a whole big source that we can keep source transforming to get this into a more convenient form. So here's a redrawn version of that circuit that I can erase and fill in the source transformations as necessary. The first practical source that I see is right here, a 20 volt voltage source with a 10 ohm resistor in series. So I can transform that into an equivalent current source model by saying that I sub S will equal V sub S divided by R sub S. In this case, 20 volts and 10 ohms, which will be equal to 2 amps. So now I can erase the old part of the circuit and fill in the new part of the circuit that has been transformed. And now conveniently, the 10 ohm resistor and the 15 ohm resistor are in parallel, and those combine to form a single 6 ohm resistor. So now I can source transform back after combining those resistors. This is a practical current source and can be transformed back into a practical voltage source by saying that V sub S will equal I sub S times R sub S, which is 2 amps times 6 ohms, equaling 12 volts. So now I erase the old part of the circuit I fill in the new part of the circuit, and now, as you can see, the 6 ohm and the 14 ohm resistors are in series and can be combined. So I will combine those into a single 20 ohm resistor. And now I'm left with just a simple voltage divider circuit, which means that V sub X is equal to 12 volts times 20 ohms divided by 40 ohms, which is equal to 6 volts. So source transformations can be a really easy and reliable way to solve a lot of circuits as long as you're only concerned with the behavior of a load resistor. So that means that all of the nodes that were in the original circuit have now disappeared, but I wasn't concerned with them anyway. So you have to make sure that you don't ever perform a transformation that will get rid of nodes or branches that you actually need to solve for. Because I didn't need to solve for anything in the original circuit that I transformed away, it was all fine. So you just have to be aware of that. This is a very powerful tool and can make it really easy to solve circuits, but you need to know when to use this tool and when not to use this tool.